So let's study neurotransmitter. First neurotransmitter. Let's see Otto Levy. Otto Levy was a guy, and he had a dream of an experiment, and he did this experiment after he woke up, and then he found the neurotransmitters. Right. So your dreams can be, they're amazing. Cool. Just read about it. Who was Otto Levy? And what was his story? So neurotransmitter. It's not love, it's neurotransmitter. I always think this because all of this emotions, sadness, depression, love, excitation, depression, everything is governed by neurotransmitter. You do some, I don't know, you do some MDMA and you feel amazing, and you are just experiencing something called as neurotransmitters. And if you see something bad and you feel depressed, it's just your levels of serotonin, dopamine are just depressed. And it's not depression, it's neurotransmitter. It's not love, it's neurotransmitter. It's the emotions, everything in your life is dependent upon neurotransmitter. If you have good neurotransmitter, good flow of neurotransmitters in your body, then you will be balanced guy. Because all sort of emotions are important in human body, and if you're just experiencing bliss all the time, happiness all the time, then this happiness will be norm for you. This happiness will become normal for you, and then this normal will eventually, happiness will become your basal feeling, and then happiness will no longer be happiness. So you need to feel little bit of what do we say, depression, right? Because if you don't feel the low, you will not feel the high, and we need this sort of going on so that our average is here. If we are always here, then this becomes our basal. So in short, neurotransmitter, it's not love, it's not depression, it's neurotransmitter. I always say this. Cool. How can a substance can become neurotransmitter? We can call a substance a neurotransmitter on the basis of three things. First, if the substance is synthesized in presynaptic neuron and it is released in the cleft, and it should have a receptor on a postsynaptic neuron. So that's the story of it. If a substance is synthesized in the body, we can call it neurotransmitter, but it has to be released in the cleft as well, and it must have a receptor on a postsynaptic neuron as well. It has to complete all these three things. Cool. What is not a neurotransmitter? Well, if a substance is not synthesized naturally by your body, and if a substance is synthesized but is not released, and if a substance is released and synthesized but is not received by a receptor at postsynaptic, all three situations have to follow. Okay, what about the classification? Classification is class 1, class 2, class 3, class 4. Class 1 is the oldest, class 2 is relatively new, class 3 is new, and class 4 is just recently. Class 1 is acetylcholine. Acetylcholine is the basic neurotransmitter for contraction, and for contraction we need acetylcholine and calcium. Class 2 is biogenic amines. So amines which are made biologically from your body, in your body, that are biogenic amines. Class 2 is amino acids. Class 4 are gases. So note, all of these classes are synthesized in your body. They are released in the cleft, and they are received by postsynaptic neurons. Let's talk about acetylcholine first. Where are they found? They are found at 4 places: 1, 2, 3, and 4. Cool. Acetylcholine is found first as neuromuscular junction for contraction. This is the basic work. Second, it's found as nucleus basalis of Meermuth. And this nucleus basalis of Meermuth is for memory. M for Meermuth, M for memory. And if this is messed up, you will get something called as Alzheimer's disease. So you need to have good levels of acetylcholine, because if you don't have acetylcholine, you will have Alzheimer's. A for Alzheimer's, A for acetylcholine. You need acetylcholine for a good sleep, and something called as REM, random movement of the eye. This is a part of the sleep where your eyes are moving randomly, and this is where you're dreaming. So this is a deep sleep, and so for deep sleep you need acetylcholine as well. For sweat glands, so at sweat glands you have something called as sympathetic cholinergic neurons, not neurons, receptors or neurons. And this neurons, they release exocytosis of acetylcholine. Exocytosis means the acetylcholine is getting out, and we need something called as snare proteins, right, to perform exocytosis. And we need calcium ions, right? So snare proteins there are 4 proteins: synaptotagmin, synaptobrevin, synaptotaxin, synap25. So B stands for Botox here, because that's how we remember. So this is just functioning of the snare protein. I am not sure if you need this, but I still explain it to you. Snare protein, if your snare proteins are not working nicely, you will have flaccid paralysis. And how you can get flaccid paralysis? You can get flaccid paralysis by using Botox. And because Botox messes up with synaptobrevin, and these protein we need for the exocytosis of acetylcholine, and acetylcholine results in something called as contraction. So we are indirectly, with the help of Botox, we are indirectly inhibiting contraction, right? Okay, so acetylcholine uses something called as 2 receptors. What are these receptors? They use it nicotinic acetylcholine receptor and muscarinic acetylcholine receptor. Nicotinic are ionic, and muscarinic are G-coupled protein receptors. G-coupled protein receptors are chemicals. They have certain domains, alpha, beta, and delta domain, intracellularly, not extracellularly, intracellularly. So these are chemical based, these are ion. Chemical based are slow, and these are fast. Cool. So we know acetylcholine now. What about class 2? Class 2 are dopamine, norepinephrine, epinephrine, serotonin 5-hydroxy, histamine, and we have that's it, right? What about the story? The story is dopamine makes, with the help of what? Dopamine beta hydroxylase. That's very important. Dopamine makes norepinephrine. Cool. Norepinephrine is a neurotransmitter, right? So this dopamine beta hydroxylase makes norepinephrine, and this norepinephrine is released at locus coeruleus. Cool. And this locus coeruleus keeps us awake and wakefulness. And this locus coeruleus is a widespread. It's not focal. Note this. So locus coeruleus is released at this place. Norepinephrine is released, and this results in wakefulness. This is why you don't want to, like, when you're stressed, a lot of norepinephrine is released, and where it's released at locus coeruleus, and you cannot sleep at night because you're really stressed. That's why you cannot sleep at night. Cool. Let's look at so this was norepinephrine. Okay, well, let's look at dopamine pathway, the biggest, the very famous, it's very famous now. Dopamine pathway, there are 4 major pathway: nigrostriatal, mesolimbic, mesocortical, and tuberoinfundibular pathway. First, nigrostriatal. So in the Parkinson disease, what is Parkinson disease? I will tell you. At the basal ganglia is this base and a gang of neurons. That's it. At basal ganglia. In the basal ganglia, there is something called as substantia nigra. This is a substance, and it's black. It looks black. So that's why they named as substantia nigra. So in basal ganglia, in substantia nigra, if the level of dopamine drop, you will have something called as bradykinesia. What is bradykinesia? Brady means slow, kinesia means movement. So your movement of your whole body will be very slow and very incoordinated. We call this Parkinson disease, right? What about mesolimbic? Limbic means some sort of emotions, right? Not this limb, not the hands one. I will tell you. Mesolimbic is a pathway. It's present where it's present. It's present at ventral tegmental area. It's a reward pathway, and that's how you get addicted to drugs. That's how you get addicted to person. That's how you fall in love. That's how you fall out of love. If you have less dopamine levels at this level, you will eventually fall out of love. You will eventually fall out of addiction. And if you have great dopamine pathway, great levels of dopamine levels at this area, ventral tegmental area, you will have something called addiction. So if the level of dopamine reduce at nucleus accumbens. This nucleus accumbens is present where? At ventral tegmental area. So A for accumbens, A for addiction. So if dopamine levels are decreasing, the addiction will go away. If the dopamine levels are increasing, the addiction will stay, or addiction will increase, or you will get an addiction. So that's the story of addiction. What about mesocortical? Cortical means brain, right? Cortical means think. So this is prefrontal cortex. Your brain is like this, okay? Here's your eyes, here's your nose, okay? Here's your mouth. So this is your brain, right? This area is prefrontal cortex. It is responsible for making decisions, and this usually develops after 25 of age. This develops after 25. So usually that's why boys, in girls it usually develops earlier. It develops around 21 or 20. But in boys, it develops eventually after 25. So most of the time, the boys actually mature after 25. So this prefrontal cortex is responsible for something called as motivation, emotion, decision, and memory. Cool. So if you don't have dopamine there at prefrontal cortex, you will have less motivation, less emotions, less decision making, and poor memory and poor decision making skills eventually in your life. So that's why you should not do any sort of drugs, any sort of brain altering drugs. For example, even MJ. What is MJ? Marijuana. Even if you do a little bit of not a little bit, if you do a lot of marijuana before the age of 25, this will hinder, this will stop the development of prefrontal cortex. So you must not smoke before 25. If you're smoking, if you're doing drugs before 25, you will have bad development of prefrontal cortex, and then you will have bad motivation, generally bad life, So you don't want that. What about tuberoinfundibular pathway? Well, there's something called hypothalamus. Well, there's something called as thalamus, first of all. Thalamus is this area, okay, in the brain. It's in the middle. And in the thalamus, there is something called hypothalamus. This area is just below thalamus. So that's why we named it hypothalamus. So at hypothalamus, this dopamine is released, right? And this dopamine goes to anterior pituitary. Pituitary is like this sac, just below hypothalamus. And this is thalamus. So this is thalamus, this is hypothalamus, and this is pituitary. This is anterior, this is posterior. Cool, we know this. So this dopamine is released in hypothalamus. It goes to anterior pituitary, and this anterior pituitary stores a lot of prolactin as well. Prolactin is the milk forming hormone, right? There are two types of hormone, milk forming and milk let down. If you press a nipple, milk will drop, right? Milk will come out, right? We call this let down of milk. And then there is something called as formation of milk. So prolactin is the formation of, lactin, and pro means before. So before lactin, that's it. So dopamine is the natural elevator of prolactin. Cool. Your body makes dopamine so that it can stop prolactin. Because in men, if you have more levels of prolactin and less level of dopamine, you will start lactating. Trust me. Cool. What about the receptors? Receptors are D1, D2, D3, D4, D5. All are G-coupled protein receptors. These are chemical receptors. These are not ionic. These are slow receptors. Cool. So we are done with dopamine, norepinephrine. Cool. Let's start with serotonin. So serotonin, amazing receptor. Do you know about magic mushrooms? Magic mushrooms. We call them magic mushroom because they are psilocybin mushrooms, and they will put you in an altered mental state of hallucination, and not even like just visual hallucination, even audio, even visual, like different, amazing psilocybin. And these psilocybin mushrooms, they actually are quite similar to serotonin. So where is serotonin made? Well, they are made at three places. RAF nucleus. Again, serotonin helps in wakefulness at this RAF nucleus of this brain, and at GIT. Wait, let me add GIT here. GIT. So RAF nucleus, wakefulness. In GIT, peristalsis of GIT, they are amazingly, serotonin is also found at platelets. And what serotonin does at platelets is that it results in aggregation. What is aggregation? It's just platelets are coming together. That's it. They are not sticking with each other. They only stick with each other at certain time, and we call that adhesion, not aggregation. Aggregation is just platelets are coming together to form a platelet plug. That's it. So we need serotonin for aggregation of platelets. That's very important. What about the receptors of serotonin? We have 7 type of receptors. From receptor 1 to 7, they are G coupled chemical, but the 5th one is ionotropic. So what does it mean? It means the 5th receptor is ionic. It means it's fast, and the rest of them are slow receptors. What about the function? Well, function is function of receptors from 1 to 7, 2A, 2C, 3, 4, and 6 and 7, right? 2A for platelets, 2C for GIT satiety. What is satiety? Feeling of fullness, yeah. So serotonin at 2A works for platelets, serotonin at 2C work for GIT. Serotonin at 3 is area postrema for vomiting. If you have a lot of serotonin at this area postrema, you will keep vomiting again and again. It's ionotropic. It means it's fast. Why God gave ionotropic? Because at these things, at 2A, 2C, 4, 6, 7, these are G coupled protein receptors. But at 3, this is ionotropic. Oh, I told you wrong. Sorry. So first to 7 is GPCR, and the third one is ionotropic. I was so wrong. I am so sorry. So from first to 7 are GPCR chemical, and third one is inotropic. So third one is inotropic. And why God gave us this inotropic? Because God knows that, not God, it is that the nature knows that if you ate something stupid, you wanna vomit this. So this is very important, vomiting, because you don't want to eat some poison, right? You don't want to eat some toxin, right? So that's why it's fast. It's lightning fast. It's ionic, right? It cannot wait for you to go home. You need to vomit fast, right? So that's why 3 number is for vomiting, and it's inotropic. What about 4? 4 is GIT. It can wait for you to go home and then start the peristalsis. What about 6 and 7? 6 and 7 is for the limbic movement, emotional. Limbic system is for the emotion. You can cry home once you go back home, right? Okay, it can wait, but the third one cannot wait. You need to vomit fast because you have eaten something very stupid. Okay, other one, histamine. Histamine is produced at 2 places, 1 and 2. First one is posterior hypothalamus. It makes wakefulness. We can stop this wakefulness by using antihistamine, anti-allergic. Do you know some anti-allergic drugs? Do you know some? I know a lot of them. For example, I know cetirizine. Cetirizine is very common. They say cetirizine makes you sleep. It's true. It can make you sleep because it inhibits histamine. Another drug called as chlorpheniramine. These drugs also inhibit histamine, and this drug makes you sleep. So this drug makes you sleepy. Sleepy Joe. It makes you sleepy Joe. That's it. What about stomach? Histamine actually works on parietal cells of the stomach, and then this parietal cells makes acid, HCl. So the more histamine, the more HCl, the stronger your HCl. Cool. Histamine makes a wakefulness and acid. Okay. So other one is amino acids. We have 3 amino acids: glutamate, GABA, glycine. Glycine, we know it inhibits something. What does it inhibit? It inhibits alpha motor neuron, and glycine is responsible for feedback inhibition. Okay. Glutamate is excitatory, except at one place called NDMA. No, I'm so wrong. Glutamate is excitatory except at one place called subthalamic nucleus. Subthalamic nucleus means I told you, hypothalamus, thalamus, pituitary. Here is thalamus, and there is one nucleus here in thalamic area, and it's called subthalamic nucleus. And all of these, neurotransmitter at this nucleus are inhibitory except glutamate. Okay, so hippocampus, the memory, short-term memory. If you have bad glutamate levels, you will not be able to sustain memory. Subthalamic nucleus, again, all neurotransmitters are inhibitory except glutamate. Glutamate is positive. It increases the positive electro charge of the cell. What about alpha A delta fibers? So we have fibers, a lot of fibers. We have around A alpha, A beta, A gamma, and A delta. Then we have B fibers, and then we have C fibers. A fibers are highly myelinated, highly fast, very fast fibers. B are intermediate, and C don't have any myelation, so they are very small. B are very highly B are like intermediately myelinated, so they are like state highways. A1 are fast, they are like national highways, and C are like the village roads, or maybe the roads between your, I don't know, in your locality, I don't know. So A delta, they are used for fast pain, because this is an A. So A delta fibers for fast pain. So glutamate also responsible for fast pain. Glutamate receptor, there are two types of receptors for glutamate, MPAR and MDMA. NMDA, not MDMA. NMDA receptors and AMPAR. So I will start with NMDA receptor. This is a calcium channel and this is a sodium channel. I will tell the story about it now. So NMDA receptor only works when glycine binds to NMDA receptor. Once the glycine binds, the calcium influx can start. Cool. Now this glycine has to bind with NMDA, but this receptor can be blocked with Mg, because Mg sits on the place where glycine should sit. It's an antagonist. But this antagonist, so just imagine glycine has binded with the NMDA, there is calcium influx. The calcium influx will result in further pathways of the cell, whatever it is. And if there is over influx of calcium, we call this excitotoxicity, because calcium results in contraction. So excitotoxicity. And where it is seen? It is seen in amyotrophic lateral sclerosis, ALS. Cool. So NMDA can lead to ALS if Ca is highly influxed in the cell, right? And fortunately, we have this drug called riluzole, and it blocks NMDA. So we have something called as Mg here. If Mg, magnesium, sits on NMDA, this NMDA stops, and we don't want to stop NMDA, right? How can we stop this Mg? We can stop this Mg using MPAR receptors. So MPAR receptors are sodium receptors, sodium channels. What happens is that once MPAR receptors bind with glutamate, lot of sodium comes inside the cell. What happens after this depolarization of the cell? Because cell is negatively charged naturally. Cell is 70 millivolt naturally. It sits here. And once sodium come inside, the cell will go into depolarization. It will, from minus 70, it go to minus 40, right? And this is the threshold. So this threshold removes magnesium from NMDA receptors. And then once the magnesium is removed, glycine can naturally bind to NMDA receptors. And then once glycine binds, the calcium can influx. And once calcium is in flux, further pathway can occur. Cool. But if the calcium is highly inside, it can lead to something called as ALS. And we can stop ALS by riluzole. Cool. Okay. Now we know glutamate. Other one, GABA. GABA is inhibitory. Always remember this. GABA works using chlorine. So GABA is inhibitory. Make the cell hyperpolar. Hyperpolar means minus 70 millivolt. Using influx of chlorine ion get inside, and then the cell will go around minus 130 or maybe minus 90. So it's hyper negative, right? Minus 90. Where GABA is found? GABA is found at basal ganglia, right? G ganglia, G GABA. And there is something called striatum in your brain. Open your anatomy and look for a striatum. It's made up of two things. So at this striatum, GABA is found, and then GABA inhibits involuntary movements of your body. For example, a lot of involuntary movements are there in your body. You keep, moving your hand, right, when you're stressed. So this is one of the involuntary movement. So what happened when you're stressed? The levels of GABA decrease, and then involuntary movement increases. Again, if you have some sort of disease, some sort of lesion in this area, in this striatum, the GABA levels will decrease, and then it will result in something called Huntington chorea. Chorea is choreography of your body, the movement. So less GABA equals to Huntington chorea. Cool. What about glycine? We know glycine can positive and negative. Negative is, I think you remember, negative is glycine works negatively for alpha motor neuron. We call that feedback inhibition. Cool. What about positive? We know positive, where it positive works for NMDA receptors. Cool. So for alpha motor neurons, Rancho cells make glycine. Glycine inhibit alpha motor neurons because we don't want alpha motor neurons to fire again and again and again without any security guard. So we want these alpha motor neurons to be in control, and we call this feedback inhibition. Okay, what about its antagonist? Antagonist is like something that takes place of the glycine, and then glycine cannot bind to that specific receptor, and then the function is inhibited. So antagonist of glycine, we call that strychnine. Glycine, strychnine. Strychnine is a poison. It's a toxin. Okay, it can inhibit glycine. Once glycine is inhibited, the alpha motor neurons increase, right? Lot of alpha motor neurons. So it will result in spastic paralysis because alpha motor neurons is responsible for contraction. How they contract? With the help of acetylcholine. So glycine inhibits alpha motor neurons, keeps alpha motor neurons in check. If glycine is messed up, your alpha motor neuron is messed up, and it will result in spastic paralysis. Now the question is, what is titanospasmin? Well, titanospasmin inhibits GABA, and we know GABA inhibits involuntary movement. So once GABA is stopped, spastic paralysis will result. So stopping GABA can result in spastic paralysis and Huntington chorea. So remember that. Spastic paralysis is a result of two toxins, different mechanism. Strychnine toxin works by inhibiting glycine, and titanospasmin toxin works by inhibiting GABA. They both are not related. Know this. Okay. What else? So we know histamine, serotonin, GABA, glycine. We know dopamine. We know Parkinson. We know norepinephrine. We know REM. We know sweat glands. We know nicotine, muscarinic. We know acetylcholine, dopamine. Okay. We know this. The gases are left. Okay. Gases. Fourth, nitric oxide, carbon monoxide. Nitric oxide is made from something called as arginine, and at the place of hippocampus, at presynaptic neuron, this nitric oxide is made, and then this nitric oxide results in glutamate formation. And we know glutamate is excitatory. It excites. It makes the cell membrane positive. And we need glutamate for good learning and memory, right? We need it. We need because glutamate works on hippocampus. And if glutamate is not working on hippocampus, you will have bad memory and then you will have bad learning. So we need good levels of glutamate. What about carbon monoxide? Well, carbon monoxide is made from heme. It's made from heme, and usually the end product of heme is carbon monoxide, and it is made by one enzyme. It's called hemooxygenase 2, because I don't know, because it's an enzyme, and without this enzyme carbon monoxide cannot be made. And again, carbon monoxide is very important for learning, memory and smell, olfaction and even pain. So you need this for learning. So we can say that for learning we need glutamate, for learning we need nitric oxide, right? For learning we need dopamine, right? For awakefulness we need serotonin and histamine, and even dopamine. What else? Norepinephrine, very important for being awake, for being stressed, because norepinephrine is a stress one. So locus coeruleus keeps us awake. So this was neurotransmitter.